welcome to this video where we are looking at kinetic theory. So this topic then, objectives for this topic are, we're going to try and understand the concept of pressure. We're then going to describe how the behaviour of gases under changing conditions. We're going to try and explain it using molecular model theory. We're going to then describe how this behaviour leads to a concept that's known as absolute zero. Or understand the ideal gas equation and use it then to calculate the state of gases. And we're going to understand what specific capacity and specific latent heat are and use them to calculate energy transfer in a material as it gets heated. Okay, so here are our useful YouTube videos that go with this. If you're watching this video on YouTube, a link to all of these will be below in the description. Don't forget Seneca as well. Make sure there's a link to that. If you can't find the link, go back to video 1. It's in that one. Okay, so let's start off. Let's talk about heat and temperature. So heat and temperature in everyday life are used interchangeably, but in physics we have specific meanings for these things. Okay, heat is a type of energy. It's measured in joules, and it's a measure of the total kinetic energy all the molecules in a material have. Basically, we add up every single molecule's energy and that gives us the heat. Whereas temperature is related to the average energy per molecule of the material. So basically, what does that mean? Well, it means that an object can have a lot of heat energy but not a high temperature if it contains a lot of molecules. So the classic examples are bathtub of water. So a bathtub of water at like 30-40 degrees Celsius will have a huge amount of heat energy compared to something like a match that's just been lit. But because you've got so many more molecules in that bathtub, it has a very low temperature. Okay, so pressure then. So gas particles move randomly. Hopefully remember this from earlier on in this unit or key stage 3. So gas molecules will move randomly, making sure they fill the container they are in. This means that every now and again they actually collide with the walls of the container they're in. Now whenever they collide, they exert a force on these walls. Okay, the faster and the more often these collisions happen, the more force they exert. Now we call this force pressure. And we can see in the triangle below me that pressure is going to be force divided by area, and it's given the units of Newton per meter squared, which we can actually convert to pascals. Now take care in an exam, they might not use pascals, they'll probably use kilopascals if it's an everyday pressure, or you might see that it's newtons per centimeter squared, and you've got to convert that to meters squared. Now, on converting square units, don't forget it's the conversion squared. So there are 10,000 square centimeters in a square meter because it's 100 by 100. There we are. Okay, so behaviour of gases. Behaviour of gases depends on 4 things: the temperature, the pressure, the volume, and how much gas is present. However, that last one we can forget about for GCSE. We don't worry about moles in physics, you do them in chemistry, we don't worry about them in physics, so you can forget about that one. Okay, so this recording's the next few slides that we've got on this PowerPoint. Unfortunately, with using this FET, it won't let me do recordings direct onto the slides. Because you need to be able to play along with this. On YouTube, obviously you'll see the slides, or you'll just see this. What you won't see is the slides afterwards. Okay, so behaviour of gases then. So if we go to laws here. So if we increase the temperature on this, let's put some gas in here. So if we put some gas in this box, here's some gas in this box. Okay, so first things first, we'll let the gas just get itself ready, so it's not just being pumped in, so it's behaving like a gas. We've got a nice mixture of speeds, we've got a nice spread of molecules all the way around our box. There we are. and we'll wait for the pressure to equalise and the temperature to equalise. So if we increase the temperature of this gas, and if we first try and keep the volume constant, so this is a sealed box, not getting any bigger, not getting any smaller. If we heat this gas up, what is going to happen is that you should be able to see that on average these molecules are speeding up. They are getting faster and faster and faster. And what does that mean? Well, that means that they are hitting the edges more frequently and with more force. Okay, and what this means then, our pressure will slowly increase. The faster and faster and faster these go, the more and more pressure we will have, because they are colliding with the walls with more frequency and with more force. Okay, if we just cool this gas back down to a sensible value again, let's go back to where we started, about 300 Kelvin. Come on, back down to 300 Kelvin. Okay, it's about 300 Kelvin. If this time, if we keep the pressure constant but vary in the temperature, if we keep the pressure, no, what do we want? We want the pressure to remain, yeah. So we want the pressure to remain constant, but the volume can vary this time. So if we heat it up, we can see that in order to keep the frequency between these collisions the same, as we have applied more heat, as we try to heat this gas up, the volume's got to increase. Okay, so we increase the temperature of a gas, its pressure is going to increase if we keep its volume constant, because we're increasing the speed with which the molecules move, so they hit the walls with more force, more frequency, increasing pressure. If we want the pressure to remain constant, then we must increase the volume so that we have the same frequency of collisions even though the molecules are moving faster. Okay, let's have a look at the next slide then. So if we change the volume of the gas, let's put some gas in here again. Put a bit of gas in here again, and we'll just let it, like we did before, just let this gas mingle around. So this time, if we increase the volume of the gas, we're increasing the space with which the molecules have got to move, and this will make our particles collide with walls less often. Now, if we keep the temperature of the gas constant and we change the volume, let's increase the volume to here, then straight away our pressure has to fall, because the molecules are still moving around with roughly the same speed, but this time they've now got more space, so therefore they hit the walls less often, reducing the pressure. Right, if we go back to our volume we had. Okay, now this time, if we keep pressure constant but vary the volume, we can see that to keep that pressure constant, we've got to add more heat in, right, rising the temperature of our gas, so that those molecules move quicker, so they collide with the wall with the same rate as we had before. Okay, and then our third one then. So just whilst we're getting this up, oops, too far. Okay, now this demonstration isn't very useful for pressure, but you can use the same reasoning as if we change pressure. So if we increase the pressure of a gas, this makes the particles collide with the walls more frequently. So if we keep the temperature constant, this is going to make the walls expand. Yeah, more force on them, they're going to expand out. If we keep the volume the same though, what we will get now is the molecules end up moving faster, because they're going to collide with the walls more often, or are colliding with the walls more often, and this is going to increase the temperature of this gas. Okay, so if we plot a graph of pressure or volume against temperature, we will get a straight line. Now this is something you could do using the previous animations from PhET, but trust me, you get a straight line. And if you extend that line, if you extrapolate that line back to zero pressure or zero volume, depending on which way you've done, you always get around, or you should get the same value if you've done it accurately enough, of minus 273 degrees Celsius. Now this temperature is defined as absolute zero, the lowest possible temperature that there is. Okay, now we then define this as 0 Kelvin. And this gives rise to a new temperature scale, the Kelvin scale. So the Kelvin scale starts at 0 and increases at the same rate as degrees Celsius. So a change in Kelvin is exactly the same as a change in degrees Celsius. If you go up 10 Kelvin, that's going up 10 degrees Celsius. However, where the two differ is if you go up in multiples. So if you double your Kelvin temperature, that's not a doubling of the Celsius temperature, and this is something that you need to be careful with. Now, to convert from Celsius to Kelvin, okay, to convert, what we do is we just, if we're on Celsius and we need to get to Kelvin, we add 273. If we're the other way around, we take away 273. Alright, so the temperature in Kelvin equals temperature in Celsius plus 273. Okay, so ideal gases then. So we can combine all the behaviours of ideal gases into one equation. The equation here, PV equals nRT. Now P is pressure in pascals or newtons per metre squared. V is the volume in metres cubed. Okay, and that's in metres cubed, so it's important that you work in the correct unit there of metres cubed. So sometimes you'll be given the volume in other units and you need to convert. Now, just like I was talking earlier with pressure, if it's metres cubed, then it's 3, it's the multiplication factor to the power of 3. So centi, 100, so to go from centimetres to metres, you would divide by 100. If you're going to squared, you divide by 100 again. If you're going to cubes, you divide by 100 3 times. So there are 1,000,000 cubic centimetres in a cubic metre. So that's something to remember here. T is temperature in Kelvin. Again, remember, we've got to work in Kelvin. The reason why we have Kelvin is this is a temperature scale with no negatives. If we double the temperature in Kelvin, we double the energy in our gas, and that's the only way this formula works. Now, N and R are constants, which for GCSE we don't worry about. N is the number of moles, and we're always dealing with fixed amount of gases at GCSE, and R is a molar gas constant, just there to make this formula work. So we change this formula to be as written now, PV over T equals constant, and this is what you will see on your data sheet on the equation page of page 2. Okay, so using the ideal gas equation, how do you do it? Well, in this format, PV over T equals constant, pretty useless. So we can rewrite it like this. Because any two things that are equal to the same thing, we can make equal to each other. So that's what we've done here. So this is the gas and the pressure and the volume at situation 1. And then this side is the gas, the pressure and the volume, the pressure, the volume and the temperature at situation 2. So the little 1s just mean the starting pressure, volume and temperature, and the little 2s just mean the finishing pressure, volume and temperature, and that's all those subscripts mean. They're just a way of us showing that it's pressure at time 1 and then pressure at time 2. Now, quite often when you come to use this formula, one of pressure, volume or temperature will be missing. So if it is, assume that it stays the same and you can just cancel it out of the equation. Okay, so specific capacity. When we heat a material up, it requires energy. So this is where we're talking about any material, whether it's a solid, liquid or gas, it requires energy. And the amount of energy required to see any temperature change depends on the makeup of this material. And we call this its heat capacity. Now, specific just means per unit mass. Whenever you see specific on something, we just mean per unit mass. So you take the heat capacity, divide it by the amount of mass. That's the specific heat capacity. Now, the definition, you need to learn this, okay, is the amount of energy required in joules to heat 1 kilogram up 1 degree Celsius or 1 Kelvin, because remember we said that's the same. Now as a formula we write it like this: Q equals mc delta theta. Now we're introducing here 2 Greek letters. Now the delta, that just means change. I don't know how well people can see the end of that because it's gone a bit dark, but delta just means change. Now we use theta here to mean temperature, and the reason we use temperature is because quite often when we're using this formula we also have time involved, and it just makes it easier if we use a theta. Oh, there we are, written it again. So yeah, so we have Q is heat energy in joules, M is the mass in kilograms, C is our specific heat capacity in joules per kilogram per degree Celsius, and delta theta is the change in temperature, your finish temperature minus your start temperature. Now, it doesn't matter whether you work in Celsius or Kelvin here, because the change in both will be the same. Okay, latent heat then. So, when a material is heated to a phase change, basically a posh way of saying melting or boiling, the heat required, there is heat required for this change to happen. It's called latent heat, and latent means hidden. Why is it hidden? Because adding this heat doesn't change the temperature of the material. So from the outside, we don't see what effect the heat is having. But this heat is required to break the bonds within the material. So when we boil something, which is called vaporization in this case, that requires a lot more energy than melting. Because when we're boiling something, we're breaking all the bonds between the molecules or the particles of the material. Whereas when we're melting, we only break a few of them. Now, to calculate this, we use this formula, Q equals mL. M is the mass in kilograms, and L is the latent heat in joules per kilogram. Okay, heating curves or heating graphs. So this is what we call a heating curve. The bottom axis can be either time or energy added, because they end up being the same thing, and the vertical axis is always temperature. Now flat lines, like here and here, they correspond to the temperature that is the melting point and the boiling point of the material. And they're flat lines because although we're adding energy, we don't see any temperature range, because this is where we have the latent heat being involved. Okay, so over to you. So like you've done in the last few of these, there is a link in the description below if you want to print these off if you're watching this on YouTube. If you've got the PowerPoint version, stop the presentation. If you click on this document, it will load up and attempt these questions. Hello, okay, so this one, let's just tidy a few things up. So we're looking here at kinetic theory now. Okay, so we're going to go through some questions on that. So, we've got a classed experiment, fixed mass of air, changes when it's heated. So we've got temperatures, we've got volume of trapped air. It's going to ask us to plot a graph. Note the scale on the volume does not start at 0. So they've given us the scale on the volume starting at 18 and the temperature. So 3 marks. It's going to be 1 for getting your scales right, 1 probably for your points, and 1 for your line. Okay, explain using your graph whether the students can take a volume reading from the syringe at 100 degrees Celsius. So we need to plot our graph, and what we will see from our graph here is, let's just hold this in the right place, we will see that actually if we continue our line of best fit up, we're going to go above 25 degrees. So we are going to write no, they cannot, as the volume will be greater than 25 centimeters cubed. Okay, so no they cannot. The volume will be greater than 25 centimeters cubed. Okay, explain how, if at all, the density of the trapped air changes as it's heated. Well, density is the amount of stuff in a given volume. Well, the volume's increasing, but we're not putting any more stuff in there. So, the density is decreasing as we have the same mass of air in a bigger volume. Explain why in terms of the motion of the molecules, why the volume of the trapped air increases as the temperature increases. So, temperature increases as T increases, the molecules move faster. So, spread apart from each other. Alright, dating. Okay, so on to this part E, the eagle-eyed. Among you will notice the bit above disappeared. That's because it took me a while to think about E. You've got to see we're right at the end of this is the higher tier separate science paper. Even though this is year 10, these are the questions now that are going to differentiate really between the A star and the A grade students. This question's quite a tricky question. So let's just think about it. So we know from our graph we've got a straight line. Our straight line is y equals mx plus c. So we want to find out the value of x when y is 0. To do that, we need to calculate m and we need to calculate c. Well, m is the gradient, which is going to be y2 minus y1 over x2 minus x1. And to work out c, we rearrange this equation once we know m, and we get that c equals y minus mx. So what we'll do is we select a value for y, select a value for x, using our gradient we've calculated, and we go from there. Okay, so let's work out our gradient first. So m equals y2, so 23, take away 19.5, all divided by x2, 60, take away 10. So that gives us a gradient of, gradient's written too low, so let's write it there. Gradient of 23, take away 19.5, all over 60, take away 10. So that gives us a gradient of 0.07. Okay, so let's put that in here. So y, which one should we pick? We'll pick the 23. 23 minus 0.07 times by 60 equals 23 minus 0.07 times 60, 18.8. So now we put that into, we want to find x. So we can do that here. So x equals, move the c over first, y minus c divided by m. So minus 18.8, because y is going to be 0, divided by our 0.07, which gives us minus 18.8 divided by 0.07, gives us a value of minus 269 degrees Celsius. Now absolute 0, if you remember, is minus 273. 4 degrees out, yeah, that's fine for this method. That's pretty damn close. State the name. Well, we've just said what it is. This is absolute 0. Alright, so that's the end of that question. That is quite a tricky, that piece of calculation, let's get in the right thing, that piece of calculation here is quite a tricky calculation. But not undoable. It's going to take some maths thinking, but not that impossible once you realise what you've got to do. But yeah, it does take a bit of thinking to get there. Okay, so graph below shows how the temperature of a block of ice changes as it's heated. Refer to the graph to explain the changes in temperature and changes in state of the block of ice in terms of the behaviour of its molecules. So, let's just have a quick look at this graph beforehand. Now, they've given us some letters to talk about the different thing that's going on. So, if we label this graph up, so if we think about what's going on at A, so this is going to be melting. Well, not melting. Here we are heating up. This bit here is melting. Gone too high. This bit here is going to be our boiling. Okay, so refer to the graph to explain the changes in temperature and state of the block of ice in terms of the behaviour of its molecules. Okay, so between A and B, we are heating up solid ice. The molecules are vibrating more. Okay, then between B to C, as we've just said, this is melting. We are breaking some bonds between molecules. Between C to D, we are now heating water. Molecules are moving around each other more and more. Okay, so we're up to C to D, and then from D to E, as we said, we are boiling. So we are now breaking all the bonds between molecules. Right, to make it a gas. And then from E to F, we are now heating the molecules will be moving faster. Yeah. Got everything we need to have in there. Okay, explain what is meant. So we've got the latent heat of fusion of ice. Is that explain what is meant by this statement? So that means that to melt 1 kilogram of ice requires that amount of energy, 336,000 joules of energy. That's what that means, what latent heat means. Okay, so we have a block of ice of 800 grams, initial temperature of 250 Kelvin. Use equations from page 2 to calculate the energy required to raise the temperature to that. Completely melt the block of ice. Okay, so 2 steps to this calculation. Okay, when we're heating, we're going to use Q equals MC delta T. When we're melting, we will use Q equals ML, and then the total, we will just add these two together. Okay, so we'll do the first bit. So to work out the energy required to heat, we are going to need specific capacity of ice. We've got that, so we're going to need to know specific heat capacity of ice is 2030. We need to know the mass of the ice, which is 0.8, because in the question we're given per kilogram. And we need to know the change in temperature, so that's the difference between those two temperatures, which is 23. So that gives us an energy to heat it of, let's just find my calculator, it's gone walkabout, it's 2030 times 0.8 times 23, whoops, not plus 23, times 23, gives us an energy of 37352. So we now got that energy. Then we do this bit, we're going to do 0.8 times out 336000. Gives us a value of 268800, and then we add those two numbers together. So we add the two numbers together to give us 306152, or 306,000 joules. Now, does that answer make sense? Yeah, if you look at the graph, how much longer it took to melt compared to heat up. So that makes sense for that answer. Okay, so we now got another graph. Shows how the temperature of 0.2 grams of water changed as it's heated from 20 degrees Celsius. Describe the relationship between the temperature and time for the first 9 minutes. So for the first 9 minutes, we've got a straight line. It's not going through the origin. So we have got, for the first 9 minutes, we have got, as time increases, temp increases, or temperature, they don't like temp, so we better write temperature, temperature increases. That is our first mark. Second mark is saying at a constant rate. If it's over with, 2 marks, 1 for describing the general trend, 1 for describing whether it's how the rate changes. Write down the temperature of the water after 9 minutes. So 9 minutes can be halfway between there and there, halfway between 8 and 10, so that's 100 degrees C. Calculate the change in temperature of the water. Well, that's going to be 80 degrees C, because it's from started at 20, finished off at 100, so it's changed temperature of 80 degrees Celsius. I think I can guess where this question is going. Yeah, no surprises there. It's going to ask me then to calculate how much thermal energy was supplied. So it's going to be the mass, 0.2, times our specific heat capacity, 4,200, times the change in temperature we've just spoke about, to give us a value of 0.2 times 4,200 times 80, to give us a value of 67200 joules. Between 9 minutes and 12 minutes, the water is boiling and its temperature stays constant, even though heat is energy still supplied. State what is happening to the water during this time. Okay, for 1 mark, state what's happening, it's becoming a gas. So the energy is going into creating the gas. This must be a foundation tier question. Yes, it is. Okay. Okay, so got QER question here. The meaning of the word latent is hidden. In terms of latent heat, it suggests that the heat does something that is hidden. Okay, we got the value of ice, we got the value for water. Suggest why the word latent is used and account for the difference in the two values, 6 marks. Okay, so why do we see it as hidden? Well, we see it as hidden because we observe no temperature increase even though energy is still supplied. So that's why we think of it as being hidden. We don't see a temperature increase even though energy is still supplied. Okay, account for the difference. Well, when melting, we only break some of the bonds between the molecules. However, when boiling, we break them all. So boiling always requires more energy. There we are, that's what we need for our 6 marks. Okay, on to this question. This question was another lovely question. Real mathsy question, a bit like we've seen before, where we've got to work out how much energy. Probably in the previous spec, this would have been 3 or 4 questions split apart. Probably maybe a 3, a 2 and a 1, or a 2, 2 and 2, something like that. Instead of just giving us a 6 and saying get on with it. You're going to have to do multiple steps. It says equations, they want to see multiple steps. Basically, a few different ways around of doing this. The way I would do it, the way I would think of doing it, is work out how much energy the aluminium needs to be supplied to melt, then work out how much energy the heater can supply, compare the two, and make a conclusion from there. So let's start off first. So we're going to start off by, like we did before, we're going to work out the energy required, Q equals MC delta T. So delta, I think we use theta, don't we? Let's use theta. So we're going to work out how much energy is required to melt it. Or not to melt it, to get its temperature first. So that's going to be 500 kilograms times 900 for the specific heat capacity times change in temperature. Well, we start at 20 and we get to 660, so that's a change in temperature of 640. So that gives us an energy of 500 times 900 times 640 of 288,123,456 Now, what I'm going to do is I'm going to store that in my calculator's memory, that long number, because I'm going to need it in a minute, and it makes it a lot easier to do it if it's stored in my calculator. Then we're going to calculate the energy needed to melt the aluminium, which is our 500 times its latent heat, which is 400,000. So 500 times 400,000 is 2 and then 6 zeros. 1, 2, 3. Oh no, not 2. And then 6 zeros, then 2 and 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. I apologise, they get quite small and probably go off the page, but that'll do. I'll store that one also in my calculator. So now the total energy is those two added together. So that's going to be 488, and then now 6 zeros. 1, 2, 3, 4, 5, 6. Or because I've saved in my calculator, I can just put the two together and I get my value. Okay, so I now know my total energy. So let's work out what our heater can supply. So energy is power times time. So 87 times 10 to the 3 kilowatts times by the time in 1 hour, is it? In 1 hour. So 1 hour in seconds is 3,600. So we'll do that sum. 87 times 10 to 3 times 3,600 gives us a value of 313,200 0, 0. How many zeros? 1, 2, 3, 5. 1, 2, 3, 4, 5. Okay, and then from there what we can see is that this value is less than that value, so claim is wrong. Again, important to write claim is wrong. Not going to get us a mark, but we would lose one for not putting it. State why in practice it would take a lot longer than the time calculated above. Well, if we calculated the time we didn't, but why? Well, because heater is not 100% efficient. Heater is not 100% efficient, and we've claimed that's what we've assumed. So of our 87 kilowatts of that power, we assume that all of that power goes into our aluminium, which is not going to be the case. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.